Greetings, math friends. We're going to do lecture 2 today in the Introduction to Limits. And just to recapture what may have been lost or missed in the previous lecture, I want to start out with looking at the diagram and the definition that we have here for the limit. This limit was defined to be a real number that f of x approaches when x is close to but not equal to a particular c value. So I have the c value here. This is my value a, which is the functional value of f of x that will be approached when we approach this value from the left or the right hand side here. So we see in the definition that the function has to be defined to the right and to the left of c. Also of note is that c doesn't actually have to be the domain. In this lecture, we are going to look at one-sided limits. So we're going to make one modification to what we've stated here. This being the limit is a two-sided limit, the two sides being the left and the right-hand side. So we're approaching that c value from both the left and the right-hand side there. So you may hear sometimes the term two-sided limit being used, and that is the definition that we've given here for the limit. I've made an adjustment to my diagram slightly. I've taken away the right values of f of x because in this case there are no right-hand side values of f of x. And I've changed the label of this functional value from A to L. The letter, again, is just a variable. It's some real number. It doesn't matter what letter that you put there. I'm putting L there in this case just because I want to reinforce that the particular definition that I have currently is the left-hand limit for this function as we approach C from the left-hand side. So this is the same approach effect that we talked about last time. We're going to potentially be selecting values to the left of c and plugging them into the function f of x and seeing what functional value, what y value, what image of these x's that we are approaching here. So the definition that I have is for a one-sided limit, specifically for the left-hand limit, and we're going to use this notation. I especially need to point out right here where c is, we have kind of this superscript negative here. This is our indicator that we are going to approach this particular value from the left. All right, so this is not negative c. This negative indicator is on the other side of the term here, and it's in the superscript position. So this is not negative c specifically, though we could approach a negative real value. That's perfectly fine. If that were the case, this would be a negative in front of the c, and then also in the superscript position, we would see this negative sign. So being that it's on the right-hand side of c and in the superscript position, this is indicating we are approaching the value c from the left, looking at our x values, and we want the limit of f of x, and that is going to be L, which is a real number. All right, so in this particular case, we need the function to be defined to the left of the c value that we're looking at. C, again, doesn't have to be a part of the domain of the function. All right, and then there's a second definition that we can put out there for one-sided limits, and that's the right-hand limit. It's going to be identical to this, except everywhere that I have the word left, we're going to replace with the word right, and this superscript negative sign is going to be switched to a positive sign, and that's going to be our indicator that we're approaching from the right. All right. Now, where does the negative and the positive come from? Well, you can think about it like this. We're looking at the x-axis here. These are x values. The left-hand side of the x-axis are the negative values. The right-hand side of the x-axis are the positive values. So in this case, we're approaching C from the positive side of the x-axis here when we're doing a right-hand limit. And on the other side, we are approaching from the negative side towards the particular value C. We're approaching from that negative side. All right, so that's why we have a negative and a positive here to indicate that. Let's look at a couple of examples. Last time we looked at some examples like this, and we used function properties to help us analyze what was going on with these limits when we were given a particular function. We want to do that again, but now we only want one-sided limits, so we can approach from the left or the right as indicated, and then look at the valuation here. We're going to look at a few examples, and then I will put a few examples for you to work in on your own on the screen. Pause the video and then restart the video to see solutions so you can check yourself. One of the best ways to get better at mathematics is to practice, just like you would practice for a soccer match. You get out on the field, you run, you practice dribbling, you practice shooting. You want to practice mathematics if you want to get better at it. So you're going to have to go through the drills, the exercises, so that you perform well when you need to do some mathematics. Here's my 3 example problems that I'm going to work with. The very first one, I'm going to approach 0 from the right. We see 0 with the superscript plus sign. Again, please do not think that I've put a sign on 0. I have put a superscript to indicate which side I'm approaching from. Again, we have our classic parabola here. You can draw a sketch if you want so that you have an idea of what you're looking at. So we have something like this. So we're approaching from the right, so we're looking from this direction. We're looking from the right at the graph. So as we're approaching from the x side, we're sliding down the side of the parabola. And where are we going to approach in the y direction as we approach 0? Well, we have an intersection right here with the axes at the point 0, 0. As we are approaching from the right on the x-axis towards 0, we are also approaching the y-axis at 0. So this limit is going to be 0. Now, if you had watched the video from last time, you know that I said you could just plug this value into here for the two-sided limit and potentially find the limit. In this case, number 1 will work also. If you plug 0 in here, 0 squared is 0. So that's going to work for us. Another thing that you could do to make sure that you know what's really going on, remember, according to definition, the function has to be defined to values of the right of the value we're interested in. So values to the right of C. If I plug values to the right of 0 in, what numbers are we approaching? If I plug 4 in, that's to the right of 0, 4 will give me 16. If I plug 3 in, I'll get 9. If I plug 2 in, I'll get 4. If I plug 1 in, I'll get 1. Notice the values are getting smaller. Well, where will they go to? What are they getting close to? In this case, they're getting close to 0. All right, for the next one, I have the cubic function here. So when we look at an x-axis, we have something that does this. And in this case, we're approaching 2, and there's this superscript of the negative. So we are on the left-hand side over here. And we're looking at the axis from the left-hand side. We're approaching from this side. We see the graph is on both sides of the y-axis, and it is on both sides of the value of 2, which would be over here. So we could approach from either side, but we're specifically indicated we're approaching from the left. So what value are we going to approach? Well, just like discussed up here, we could just plug this value into here and find that we're approaching 8. So far, this seems very similar to what we discussed with the two-sided limit. But I have one more example here that really illustrates part of the definition where the value that we're approaching doesn't have to be in the domain of the function. This doesn't really completely illustrate the two-side not working for us, but it certainly illustrates the domain issue on this one, because we essentially have a straight line with a single point removed in this function. What point is removed? Well, if we look at the denominator, if I plug in the value 4, which is our specific value we're looking for, it's called C in the definition over here, I will have 4 minus 4, so I have a division by 0 issue on this. And in a classical algebra, you can't divide by 0. But remember, according to the definition, not having a point present in the domain is not a problem for limits, because we're really approaching there and we don't have to be equal to there. So we have a couple of options. You can choose values that are close to 4 but slightly bigger. Why slightly bigger? Because we are approaching from the right, so we're looking at values defined on the right hand side of this. So right of 4, we need values bigger than 4. We can plug in values bigger than 4 here. You can create a table of values for that and then see what values those are approaching. The second approach to this is we can do a little bit of algebra to make this look a lot better. And sometimes when it comes to limits, you could make a table of values. That's absolutely a valid way to do this. Sometimes a little bit of algebra will shed a lot of light on the problem that you're looking at. Notice in the numerator here, this is a factorable polynomial. You can use a variety of ways to factor that depending on your background and memory, or you could use a table of factors to look this up, but we want to notice that this is factorable. It's going to factor into two pieces, x minus 4 and x plus 4. And you can go ahead and check that if you want. You can do some double distribution and see that you will arrive back here. And then the denominator is the same here. So this function is this function. Notice that we have an x minus 4 here and an x minus 4 here. So we can look at just what happens when we plug in 4 for x plus 4. In that case, it's 8. So when we look at the limit of this, it's going to approach 8. And you can go ahead and check that. If you go ahead and graph any of these and look at the graph, as you follow the graph towards the indicated x value, you can see where that y value should exist if it is going to approach a limit. So go ahead and do the exercises at the end. Cheerful calculations.